Chapter 10, Section 5, Segment Lengths and Circles. The first theorem in this section states that if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. An illustration of this theorem would be having a circle and having two chords intersecting on the interior. Here I have chord AC and chord BD. The two segments of chord AC would be AE and EC. The two segments of chord BD would be BE and ED. This theorem states that the product of those two segments would be equal to each other. So in this case, I have segment AE times segment EC would be equal to segment BE times segment ED. An example using this theorem says that chords AB and CD intersect inside the circle. They ask us to find the value of x. If you notice, chord AB is broken into two segments, one measuring 18 and one measuring x. Chord CD is broken into two segments, one measuring 12 and one measuring 9. Using the theorem, I can say that 12 times 9 would equal 18 times x. Go ahead and multiply 12 times 9 and you get 108 equals 18 times x. To solve for x, I need to divide by 18 on both sides, and when I do so, I get 6 for x. I need to talk about a couple of different terms with you. The first term would be referring to PR. If you notice, segment PR would be secant to my circle because it goes and it touches the circle at point R and it goes through the circle at point Q. So it's touching the circle at two different parts. We would call this a secant segment. If you notice, we call it a segment because it ends at point P and it ends at point R. It is not a line that goes through. Then I have PQ. If you notice, PQ is part of the secant segment PR, but it is on the outside of my circle. So I call PQ a external secant segment. If you notice, PS is tangent to my circle, and again, it is a segment. It has its endpoints at P and an endpoint at the point of tangency S. So I call segment PS a tangent segment. The next theorem says that if two secant segments share the same endpoint outside a circle, then the product of the length of one secant segment and its external segment equals the length of the other secant segment and its external segment. An illustration of this theorem, I have two secant segments, AC and AD. If you notice, the external segment of secant segment AC would be AB, and the external segment of secant segment AD would be AE. This theorem states that the whole secant segment AD times its external segment AE would be equal to the whole secant segment AC times its external segment AB. An example using this theorem asks us to find the value of x. We know we have two secant segments, FD and DH. To find the length of the whole secant segment, I need to add the two segments of each together. So secant segment FD has two segments, FE and ED. When I add those two together, I get 21 for the length of FD. If you notice, secant segment DH has two segments measuring x and 12. So secant segment DH would be 12 plus x. The external segment of secant segment FD measures 11, and the external segment of secant segment HD measures 12. I know that when I multiply these two parts of my secant segments together, they should be equal to each other. So go ahead and set that up. Here I have external segment 11 times the whole secant segment, 21, equals 12 times 12 plus x. Go ahead and multiply and distribute, and you wind up with 231 equals 144 plus 12x. To solve for x, I need to subtract 144 from both sides. When I do so, I get 87 equals 12x. To solve for x, divide by 12, and you get 7.25 for x. The next theorem states that if a secant segment and a tangent segment share an endpoint outside of a circle, then the product of the length of the secant segment and the length of its external segment equals the square of the length of the tangent segment. An illustration of this theorem would be having a circle. I have secant segment CA and tangent segment CD. The external segment of my secant segment would be CB. What this theorem says is that CA, the whole secant segment, times CB, the external segment, would be equal to CD squared, which is the tangent segment. An example using this theorem asks us to find the value of x. If you notice, I have tangent segment AB, which measures 30. I have secant segment DA, and I know that the external segment measures x, and the whole secant segment would measure 24 plus x, or x plus 24. In order to solve for x, I need to use the theorem that states that my external segment x times the whole secant segment, x plus 24, would be equal to my tangent segment squared, which is 30 squared. Go ahead and distribute your x and square 30. When I do so, I get x squared plus 24x equals 900. To solve for this, I'm going to need to put it into standard form, which means that I get all of my numbers over on one side. So I subtract 900 from both sides. I have x squared plus 24x minus 900 equals 0. And I do this because in order to solve for x, I need to use the quadratic formula. A quick review of the quadratic formula. The formula that we use to solve for x is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You've seen this before, and you probably learned a chant to help you memorize it. So going back to solve for x, I have the formula x squared plus 24x minus 900 equals 0. Now to find a, b, and c to plug in, I use my equation. There's an understood 1 in front of x squared, and that becomes my a. 24 is what I will plug in for b, and negative 900 is what I will plug in for c. Notice because I am subtracting 900, every time I see a c, I will plug in negative 900. So plugging it into the formula, it's going to be negative 24 plus or minus the square root of 24 squared minus 4 times 1 times negative 900 all over 2 times 1. Go ahead and do the operations inside of your square root sign. you wind up with negative 24 plus or minus the square root of 4,176 divided by 2. You can plug this into your calculator. One thing that you will plug in would be negative 24 plus the square root of 4,176 divided by 2. And you could also plug in negative 24 minus the square root of 4,176 divided by 2. Because we are trying to find a distance, I'm going to plug both of those in, and the one that is positive is going to be my answer, because we cannot have a negative distance. When I do so, I end up with a positive 20.3. My next example says that you are standing 18 feet from a circular display case. The distance from you to a point of tangency on the case is about 32 feet. It asks us to estimate the radius of the display case. If you notice, this circle will represent the display case. The problem tells us that you are standing 18 feet away. So the circle represents you, and you are 18 feet away from the circular display case. It tells us that from you to a point of tangency on the case is about 32 feet. So go ahead and draw a point of tangency from you to the display case and mark it 32 feet. Now it asks us to estimate the radius of the display case. If you notice, I have a tangent segment, and then if I want to use a tangent segment in a theorem, I need to have a secant segment. So go ahead and make the line that's measuring 18 go all the way through your circle. If you notice, that creates a secant segment. It's also the diameter of the circle. We want to find the radius, though. So instead of saying diameter, I'm going to say that this part is the radius and this part is the radius. So if I wanted to find the length of the whole secant segment, it would be r plus 18. Well, r plus r can be simplified into 2r plus 18. Now I can use my theorem and say that 18 times 2r plus 18, so my external segment times my whole secant segment, will be equal to 32 squared, which is my tangent segment squared. Go ahead and distribute your 18 and square 32. You wind up with 36r plus 324 equals 1024. To solve for r, I first need to subtract 324 from both sides. When I do so, I have 36r equals 700. To solve for r, divide by 36 on both sides, and when you do, you get 19.4. So the radius of my circle would be about 19.4 feet. The assignment for Section 5 is on page 632, numbers 3 through 28 all.